So, um, imagine your digestive tract as this incredibly vast, like, intricate series of tunnels.
Right, it's basically plumbing.
Exactly, human plumbing. And for the most part, traffic just flows smoothly.
Huh.
But what happens when one of those tunnels suddenly collapses?
Or narrows down so tightly that absolutely nothing can pass through.
Yeah, you have a major roadblock deep inside the body. So today we are taking a deep dive into the mechanical precision and the intense human teamwork required to safely clear those blocked tunnels.
From the inside out.
Right, from the inside out and entirely without major surgery, which is wild to think about.
Right.
To understand how medical professionals actually navigate this, we are pulling directly from a masterclass video on YouTube by Gadamukala S. Raju.
It's a fantastic source.
It really is. The video specifically details a procedure called hydrostatic balloon dilation. And it goes into the operation of a tool that honestly sounds like it belongs on a construction site.
The balloon dilator gun.
The balloon dilator gun. I mean, it just has this very industrial ring to it, right?
It does, yeah. But the intersection of elements here is what makes this procedure so compelling to study. You know, we're looking at the application of raw, calculated mechanical pressure combined with the navigation of highly unpredictable human anatomy and, crucially, the reliance on real-time tactile communication.
So it's not just about, like, deploying a piece of medical hardware.
No, not at all. It's a really delicate management of physics inside a living person.
Okay, let's unpack the physics then and the problem itself before we even touch the machinery. Because the source centers specifically on what they call complex strictures.
Right.
We aren't talking about a simple, straightforward bottleneck in the esophagus or the colon. The video highlights narrowings that are exceptionally tight, very long, or highly angulated.
Angulated meaning bent or curved.
Yes, you're dealing with a tunnel that twists sharply while simultaneously clamping down, which effectively eliminates any line of sight.
And when you lose that line of sight, the entire dynamic of the procedure completely changes. Well, in locations like the esophagus, the pylorus, the ampulla, or, the IC valve, a blind approach is incredibly dangerous.
Because you can't see what you're pushing against.
Exactly. If an endoscopist were to simply take a standard balloon catheter and just push it into a twisting, complex stricture, the vector of force is entirely wrong.
Like pushing straight forward into a curve.
Right. You are pushing straight forward, so the catheter will bunch up or loop, or worse, it'll push directly into the mucosal wall.
Oh, wow.
Which creates shear force that can severely damage the tissue.
Which perfectly explains why the source is so adamant about using a wire-guided balloon dilation for these specific cases.
It's mandatory, really.
I mean, if you've ever tried to thread a soft string through a curved, completely dark pipe, you know the physical frustration.
Oh, yeah. You shove the string and it just bunches up.
Right. But if you send a tiny, flexible guide wire through that pipe first, you establish a physical track.
You lay down the rails.
Exactly. And then the string, or in this case, the balloon, can just slide right along that established path.
The guide wire fundamentally shifts the physics of the insertion. I mean, it removes the forward-pushing shear force we just talked about.
So the endoscopist is meticulously navigating that flexible wire through the angulated stricture first.
Yes, feeling their way through the twists. And once the wire is safely across the narrowing, the balloon catheter acts almost like a train on a track.
It just follows the precise curvature of the wire.
Right. So the dilation becomes an exercise in lateral expansion rather than forward force, which honestly is the absolute cornerstone of procedural risk mitigation here.
Okay, so the track is laid. We have a safe pathway through the anatomy. Now we have to look at the tool that generates that lateral expansion.
The gun.
The gun. The video provides a really thorough look at the back table setup and the meticulous prep involved. Because, I mean, the margins of error inside an angulated stricture are so tight.
Oh, incredibly tight.
The tools have to be prepped with literal mathematical precision. You have the balloon dilator insufflating device, the gun itself, alongside a pressure recording syringe, water, the balloon catheter, and some basic lubricants.
But the gun is the control center.
Right. So break down the mechanics of this thing for us.
Well, the mechanical logic of that gun handle is basically the foundation of the assistant's role. It operates on 3 distinct positions, conceptually mapped out like a clock face.
Okay, a clock face.
Yeah. Straight up at 12 o'clock is neutral. Pushing the handle forward engages the inflation mechanism.
Like pushing the gas pedal.
Exactly. And pulling it back to 3 o'clock engages deflation. understanding that fluid mechanical shift is completely non-negotiable for the assistant.
Because they are the ones about to manage the pressure of the entire procedure.
Yes, they are driving the pressure.
And that pressure is specifically hydrostatic, which is a huge distinction the video makes. They aren't pumping this balloon up with air, right? They are using water.
Right, saline or water.
They secure the syringe to the gun, switch between inflation and deflation, and suction exactly 35 cc's of water. But why is the distinction between air and water so critical here?
It's a great question.
I mean, if the goal is just to inflate a balloon, why go through all the trouble of measuring out exact cubic centimeters of fluid?
It all comes down to compressibility.
Okay.
Air is a gas, which means it is highly compressible. So if you use pneumatic pressure, air pressure inside a stricture, the air acts like a spring.
I see.
When the balloon meets the heavy resistance of the narrowed tissue, the air inside simply compresses before it expands the balloon.
So it builds up potential energy.
Exactly. And if the tissue suddenly yields, that compressed air expands violently.
Oh, man. So it creates this snapping effect.
A huge snapping effect. And you lose all control over the diameter of the balloon at that exact second.
Which is the last thing you want inside a fragile organ.
Right. Water, however, is an incompressible fluid. This is the core principle of hydrostatics.
So it doesn't compress at all.
No. When the assistant pushes 1 cubic centimeter of water out of that syringe, it translates to an exact, immediate, and proportional expansion of the balloon.
There's no spring effect whatsoever.
None. The transfer force is 1-to-1, giving the team absolute microscopic control over the dilation.
That makes the next step in the prep phase make total sense. Because once the assistant has drawn those 35 cc's of water, they point the gun straight up and pump the handle to expel any residual air from the syringe.
Yeah, they cannot afford even a single bubble of air.
Right, because it would compromise that incompressible fluid dynamic. But then the source highlights a step that seems entirely counterintuitive to me at first glance.
The vacuum step.
Yes, before handing the balloon over to the doctor, the assistant attaches it to the gun, points it downward, switches to the deflation position, and pumps the handle until it physically bottoms out. They pull this massive negative pressure vacuum on the balloon to ensure it is completely, totally collapsed.
I have to ask, why is it so incredibly vital to perfectly collapse this balloon before the doctor even touches it?
I mean, it seems weird, right? You are spending vital prep time emptying a balloon that exists solely to be filled.
Exactly. Isn't it just going to be inflated anyway?
It is, but the spatial limitations of the equipment demand it. The endoscopist has to pass this balloon down through the endoscope itself.
Okay.
Modern endoscopes have an internal working channel, the biopsy channel,
Yeah.
which is incredibly narrow. We are talking about hovering around 2.8 to 3.7 millimeters in diameter.
Wait, really? Millimeters?
Yes.
So you are feeding a deflated plastic balloon down a 3-millimeter tunnel, which is then inside the patient's body.
Yeah, and the balloon is wrapped tightly around its catheter, but if there's even a microscopic trace of air left inside, the balloon material will not lay perfectly flush.
Oh, it's going to bulge.
It creates a tiny, almost invisible bulge. And in a channel that narrow, that microscopic bulge introduces fatal friction. So it would just get stuck.
The catheter will simply jam halfway down the endoscope. So the assistant must pull that absolute vacuum so the balloon becomes as flat and rigid as a ribbon. It's a game of millimeters.
The video even offers this highly practical, boots-on-the-ground medical hack for dealing with that friction, which I loved.
Oh, the biopsy cap trick.
Yeah. Before the endoscopist inserts this vacuum-sealed balloon into the biopsy channel, they take a separate large syringe and physically puncture the rubber cap of the biopsy port.
Which is so clever because it bypasses the initial resistance.
Right.
The rubber cap is designed to maintain a seal so fluids don't leak out of the scope. But pushing a tightly wrapped balloon catheter through it can actually damage the balloon material before it ever reaches the patient.
So puncturing the cap creates a smooth, pre-dilated entry point.
Exactly.
And then they apply a drop of lubricant directly to that cap. I mean, it is such a stark contrast. We're talking about incompressible fluid dynamics, complex spatial geometry, and high-tech endoscopes.
And it all comes down to a drop of lube on a plastic cap.
Yes. The procedure still relies on physical lubricant to ensure the catheter slides down smoothly. It really grounds the whole highly technical process in basic physical reality.
It's a constant reminder that you are battling physical resistance at every single stage of the journey.
So true.
So the catheter slides down the lubricated channel, exits the endoscope, and tracks perfectly over that guide wire we laid down earlier.
And then it seats itself directly inside the complex stricture.
Right. And this placement can be verified visually through the scope or with fluoroscopy to confirm that the radio-opaque markers on the balloon are perfectly centered in the narrowing.
And once it's centered, the dynamic between the endoscopist and the assistant shifts entirely. Here's where it gets really interesting. This is where the choreography truly begins.
The dance, yeah.
The assistant, who is managing the back table, switches the gun to inflation and begins to slowly pump the water in. And the video points out a fascinating mechanical reality here. Once that balloon begins to fill with water and expand against the stricture, it becomes snug.
It locks itself into the tissue.
Right. The balloon is no longer a sliding component. It is an anchor.
Which creates a really complex physics problem for the endoscopist who's holding the scope.
How so?
Well, as the balloon expands, it naturally wants to slip forward or backward through the path of least resistance, like squeezing a watermelon seed.
Oh, sure.
If the endoscopist tries to adjust the endoscope, the scope moves, but the balloon stays locked. So the endoscopist has to physically grip the biopsy port and hold the catheter tightly in place to prevent the balloon from migrating out of the stricture.
Wow. Okay, so you basically have two operators managing opposing physical forces.
Exactly.
The assistant is driving the hydraulic pressure inward, and the endoscopist is acting as an anchor, holding the line to keep the system stable. And simultaneously, the assistant takes on the role of timekeeper.
Yes, the duration of the continuous radial expansion is a critical variable because tissue needs time to stretch and yield.
So they don't just pump it up and immediately deflate it.
No. The assistant starts tracking the inflation cycles the moment the balloon becomes snug. Depending on the clinical judgment of the endoscopist and the nature of the stricture, they might hold that dilation for 30 seconds, 60 seconds, or even push it to a full 120 seconds.
It depends entirely on the doctor's preference.
Precisely.
But the assistant is tracking something far more important than just the clock. And this is the mechanism that I find absolutely brilliant.
That tactile feedback.
Yes. As the assistant pumps that gun handle, pushing the water into the balloon, they are physically feeling the tactile resistance of the patient's anatomy pushing back.
It's an incredible feedback loop. The assistant's hands are the primary sensor for the entire procedure.
Right, because the endoscopist has the visual feedback. They're looking at the screen, watching the balloon inside the body.
But visual feedback cannot measure tissue tension. The assistant has their hands on the hydraulic pump, and because water is incompressible, as we mentioned earlier, the resistance of the stricture is transferred directly back through the fluid, down the catheter, and right into the handle of gun.
This is like a bizarre form of blindfolded driving.
It really is.
The doctor has their eyes on the screen, looking at the stricture, but the assistant has their hands on the gas pedal, the gun, and is feeling the physical resistance of the patient's anatomy.
It's a profound exercise in trust.
Absolutely.
Yeah.
And the source explicitly mandates that the assistant must verbally communicate this tactile data.
Yes, they have to constantly talk to each other to combine the physical feeling with the visual feedback.
If the assistant feels the handle becoming incredibly stiff, indicating that the stricture is heavily resisting the expansion, they have to speak up immediately.
Because what's fascinating here is that despite all this advanced technology, the success of the procedure hinges entirely on basic, real-time human communication.
It bridges the gap between seeing the anatomy and feeling its physical limits.
Right. The success of the high-tech equipment hinges on a human being saying, the handle is getting tight.
And that verbal cue tells the endoscopist to pause.
To pause, evaluate the visual field, and decide if the tissue has reached its maximum elasticity.
Because expanding a human organ isn't a matter of just pumping until the pathway looks wide enough. There are strict mathematical parameters governing how far you can push that tissue.
Oh, absolutely.
The source details the use of a continuous radial expansion balloon, which is fundamentally different from, like, a standard rubber party balloon.
Very different. Standard balloons are what we call compliant. You push air or water into them, and they just keep stretching and expanding in all directions until they burst.
Right.
A continuous radial expansion balloon is non-compliant or semi-compliant. It is made of specialized polymers designed to expand to a very specific, predetermined diameter based on the exact amount of pressure applied.
So a single balloon catheter can be stepped up to multiple highly accurate sizes.
Yes, up to 3 different sizes usually.
But the endoscopist doesn't just dial up to the maximum diameter on a whim. The source outlines a rigid protocol known as the Rule of Three.
This raises an important question about the delicate limits of human tissue. The Rule of Three is the ultimate safeguard against catastrophic tissue failure.
So how does it work in practice?
The protocol dictates that once the assistant feels that definitive physical resistance, once the stricture really starts fighting back against the hydrostatic pressure, the team will only upsize the balloon a maximum of 3 more millimeters in a single session.
3 millimeters.
Yeah.
I mean, that is an incredibly thin safety margin. You're talking about the thickness of a few stacked coins.
It is a deliberate conservative limit, because whether the team is using a balloon dilator or older mechanical methods, that 3 millimeter threshold respects the biological tensile strength of the mucosal layers.
The tissue can only take so much.
Yeah, right. Tissue can stretch, but if you exceed its elastic limit, it tears. The Rule of Three exists precisely to balance the need to open the pathway against the severe danger of perforation. It allows the team to achieve a meaningful widening of the stricture while staying mathematically safe.
And while the assistant is managing the math and the physical resistance, the endoscopist is performing a visual check that takes advantage of the hydrostatic setup in a really cool way.
The visual advantage is huge.
Right, because the balloon is inflated with water rather than air, and because the polymer material is transparent, the balloon acts almost like a clear lens.
Yes.
Wait, so they're looking through the balloon while it's inside, like looking through a glass window that's actively pushing against the walls of the tunnel?
That is exactly what they are doing. It is a remarkable optical advantage. When the water-filled balloon presses outward against the stricture, it creates positive pressure against the wall of the organ.
Okay.
This pressure actually blanches the tissue, temporarily pushing the blood out of the superficial capillary beds.
Huh.
And by looking through the transparent balloon, the endoscopist gets an unobstructed, brightly lit view of the mucosa as it stretches.
They are looking straight through this high-pressure water lens, watching the fibers of the human tissue react in real time.
It's incredible.
But what they are looking for dictates the immediate safety of the patient. If the endoscopist, staring through that balloon, sees a tear beginning to form in the mucosa, the protocol is absolute.
You halt immediately. There is no pushing past a visible tear.
You don't try to get just 1 more millimeter?
No. The instruction is to instantly command the assistant to switch the gun to the deflation position. A mucosal tear is the visual indicator that the tissue's tensile strength has been breached.
And if you keep going.
Continuing to apply radial force at that point will turn a superficial tear into a full-thickness perforation.
Which the source is very transparent about. They detail the adverse events associated with the procedure. I mean, minor bleeding is somewhat expected, right?
Yeah, when you stretch inflamed or scarred tissue, capillaries will break.
But a perforation, actually poking a hole entirely through the wall of the organ, is the most severe known complication of balloon dilation.
It is the exact scenario. The guide wires, the incompressible water, the continuous communication, and the Rule of Three are entirely designed to prevent.
Right.
A perforation turns a minimally invasive endoscopic procedure into an emergency surgical situation. The source also notes that patients may experience chest pain if a tear occurs, or even just during the procedure.
Which totally makes sense when you consider the sheer mechanical force being applied to the surrounding nerve networks.
Absolutely.
But assuming the dilation is successful, the stricture is widened, and the Rule of Three has been safely observed, the procedure still isn't over. The exit strategy requires just as much provision as the insertion.
You can't just yank it out.
Right. The endoscopist cannot simply pull the endoscope and the balloon out of the patient.
You run into the exact same spatial limitations you had at the very beginning. The balloon has been stretched, filled with 35 cc's of water, and subjected to massive pressure.
So it's not the flat ribbon it used to be.
Not at all. If the endoscopist tries to pull a partially inflated balloon back into that 3 millimeter biopsy channel, it will wedge itself irreversibly.
So the assistant has to execute that counterintuitive prep step one last time.
The vacuum step.
Yeah, they switch the gun handle back to the 3 o'clock deflation position, pulling the handle back until it bottoms out, drawing all the water back into the syringe and pulling a hard vacuum on the balloon.
It is a closed mechanical loop. The assistant must visually confirm the syringe has drawn back the fluid and physically feel the vacuum lock in the handle.
And only when the assistant verbally confirms that the balloon is completely, totally deflated can the endoscopist safely withdraw the catheter through the scope.
You end exactly as you began, with a perfectly flat, vacuum-sealed piece of plastic.
It's amazing when you step back and look at the entirety of this deep dive. The sheer mechanical ingenuity is staggering.
It really is.
We started with the physics of a twisting, unpredictable roadblock deep inside the body. We looked at how a simple wire changes the vector of force to ensure safety.
The train tracks.
Right. We explored the deep fluid dynamics of the balloon dilator gun, why incompressible water replaces compressible air to provide absolute precision. And most importantly, we saw how all of this advanced technology fundamentally relies on an intense, tactile feedback loop between two human beings.
Because the machinery is only as effective as the communication driving it.
Exactly.
The assistant feeling the hydraulic pushback of the stricture, the doctor watching the tissue blanch and stretch through a water-filled lens, and both of them strictly adhering to that 3mm mathematical safety net. It really reframes what we think of when we hear the term minimally invasive.
It certainly does. There's nothing minimal about the physics or the teamwork involved. The next time you hear about a medical procedure clearing a blockage, think about the unseen hydrostatics and the real-time human choreography happening behind the scenes.
It's never just a doctor looking at a screen.
No, it is an assistant holding a pressurized handle, feeling the anatomical resistance of the patient, and speaking up. Which leaves you with a final thought to ponder.
Oh, I like where this is going.
In a procedure that relies so heavily on a human assistant, physically feeling the hydraulic resistance of water pushing back into a plastic handle, how might the future of procedural medicine evolve?
That's a great question.
Like, could we soon see smart balloons or smart catheters equipped with microscopic, built-in haptic sensors, systems that automatically calculate exact tissue tension in real time?
Oh, and instantly shut off hydrostatic pressure milliseconds before a tear can even visually occur, removing the human error entirely.
Exactly.
Right.
Or is there an inherent irreplaceable safety in that human touch? The physical feeling of the anatomy pushing back against the operator's hands. It is definitely something to consider the next time you find yourself marveling at the intersection of human biology and mechanical engineering.
A lot to think about.
For sure. Well, that wraps up today's exploration. We'll catch you on the next deep dive.